before we move on to the next, the different range of the damping ratio, any questions about this graph? Good. Okay. So the second scenario I want to explore is this case. So that means the root becomes positive minus j omega n. Okay? And again, we plug in when zeta equal to 0, basically become like this. So again, for this case, let me redraw on here. If you like, you can redraw on to here, but it's not necessary. You can overlap the original drawing. So this is a complex plane. Okay, so for this case, the root located here. Simply is here and here. Okay, so that is omega n. This is minus omega n. That's it. The real part becomes 0. So the real part becomes 0, then in the time domain, we know that this is time, and this is x of t. Because the real part becomes 0, no decaying. That means oscillation keep constant. And keep constant with the frequency defined by omega n. From peak to peak or from valley to valley, the period is divided by 2 omega. Okay, no decay. So far, for the two systems, we define as a stable system. The stable system, that means the x of t is such that the x of t, its magnitude, we take the absolute value, which means we take the absolute value is finite for all possible value of t. So that's called a stable system. That means we won't expect the x of t going to explode it and keep us the finite value there. If this one, otherwise we define the system is called an unstable system. So using that definition to check against what we have learned here. So for damping ratio, underdamped system, you can see the amplitude decaying over time. The same thing, this although lower, but still decaying. So the two cases are stable system. How about for this case? Basically, this is an amplitude. Constant amplitude. So how about for this system? Is this system stable? Yes. Yeah. According to our definition, because the amplitudes keep constant, so this is still defined as a stable system. Okay. So now we consider another case. So say damping ratio equal to 1. If damping ratio equal to 1, then basically that case becomes is the root equal to minus omega n and minus omega n. Right? And two repeated roots. So for example, say, minus 1, minus 1, okay? Under this case, we know the result is equal C1 plus C2t times the exponents minus t, right? So for the solutions like this example, if we have a repeated root, so like minus 1, let me use the numbers for illustration, then we have a solution like this. Right? So solution like this, you can see this basically has a two parts, C1 minus t plus C2t times e minus t. Then let me draw the two parts together. This is, let me call the part 1. So part 1 basically is the exponential decay, right? For the second part, that is exponential decaying multiplied with a linear increasing. So let me ask you, this is a linear function, this is an exponential function decaying. This is increasing over time, this is decreasing over time. Which rate is faster? Yeah. So overall, their multiplication is still decaying because this decaying time is faster than increasing time. So combined together, they're still decaying, but the decaying rate will be slower than the pure exponential rate. Okay, so let me say the second part still decaying, but the decaying maybe is in certain way. We can numerically investigate it in more accurate, but schematically it's like this. Okay, so taking the two terms together, actually we can see their combined results still decaying over time. So again, is this system stable or not? Yes, this system is still stable. Good? Okay. Then the last case is damping ratio greater than 1. That is what we define as the overdamped systems. The overdamped system basically here the root. And for example, say let me make one example, say -1 and -2. Okay. So let me use numbers, for example. The roots will be different, distinct, real roots, okay, like this one. For damping ratio is positive, we guarantee all the roots will be negative, okay, we guarantee. And so in this case, the x of t will be c1 exponent minus t plus c2 exponent minus 3t. And again, that is the combination, summation of the two exponentially decaying functions. So definitely this is a stable system. Good? Okay. So that is for talking about here we combine the two concepts. One is the graphical representation of the roots, and that is given in one little section in our textbook, and then combining with the definition of the stability. Any questions?